Area and arc length in polar coordinates. What does the idea of area actually mean in polar coordinates? Well, let's take a look at a piece of a polar curve. So let's suppose this is a curve out to theta 1, and this is out to theta 2, and my polar curve for that particular segment looks like that. If I'm interested in the area, what I'm talking about is this area in here. So the question is, how would I calculate that? How would I come up with the area for that? Well, let's think about what we did in the rectangular plane and see if we can take that idea and transfer it to the idea of polar coordinates. If I have some function on the xy plane from A to B, what we did to find the area is we broke this thing up into a bunch of rectangles. And what we said was that the area is approximately equal to the sum I equals 1 to n of f of xi, that's the height of the individual rectangle, times delta x, where delta x was the width of any given rectangle. And let's make it simple for right now. Let's say that delta x is all the same, so I'm not dealing with delta xi's. So that would give me the approximation of the area. And then if I took the limit as n goes to infinity of the sum I equals 1 to n of f of xi times delta x, that's actually equal to the integral from a to b of f of x dx, which is actually truly the area under the curve. So how can we take that idea and transform it into polar coordinates? And it's really not hard to do. What I want to do is I want to think of this same piece, and what I want to do is, we can't break this into rectangles, but we can break it up into little wedges. So if I break this up into a bunch of sufficiently small wedges, then if I take a look at any individual wedge, I'm going to say this is out to theta I, and this is out to theta I plus 1. If I make that wedge small enough, it's essentially a piece of a circle. But I have to make it pretty small. So I know the formula, I know how to calculate the area for an entire circle, so I should be able to take the area for this little wedge, add up a bunch of wedges, and get to exactly where we need to be. So I know that the area of a circle is equal to pi r squared. Or r is pretty simple. R, what we're thinking of as r, is really going to be r of theta. It's that function of theta that the radius keeps changing in the polar coordinates. So individually, this particular wedge, any given wedge, if I say that theta I plus 1 minus theta I, I'm just going to refer to that as theta. Matter of fact, I'm going to refer to that, no, theta is okay. Let's leave that as theta for right now. I'm going to refer to that as theta. Then the area for this one piece is going to be a percentage of the whole circle. The percentage of the whole circle will be theta over 2 pi. And if I multiply that by pi r squared, obviously the pi's cancel out, and I end up with r squared over 2 times theta. That would give me the area for any individual wedge. Well, if I now think of this theta as delta theta, because I'm going to be adding up all these little wedges, I can say that the area for this polar curve between theta 1 and theta 2 is going to be equal to, or approximately equal to, the sum I equals 1 to n of, I'm going to pull the 1/2 out here, r of theta squared, because this is that function of theta that's going to be changing, times delta theta, which then tells me, or brings me to the idea, that the area will actually be equal to 1/2 times the integral from theta 1 to theta 2 of r squared of theta d theta. So I can use this Obviously, I took the limit here. I kind of skipped that part. If I take a look at the limit, sorry about that, as n goes to infinity of 1/2 times the sum I equals 1 to n of r squared of theta delta theta, that will lead me to the integral. So I can use this to go ahead and calculate areas for polar curves. So let's take a look at a quick example. I want to find the area for one petal given r of theta equals cosine 3 theta. So as an example, I want to find the area for this petal right here. That's a little problematic. We need to think about this, because when we think about starting from theta 1 to theta 2, where we're going to start and end, let me just for a moment retrace what this would look like. For theta equals 0, I'm going to be right here. Then the function is going to come, the polar curve is going to come around and look like this. So I'm all the way over here already, but I need to do this area. So clearly it's not a simple situation where it's coming around like that and making life easier on us. No, it couldn't be that easy. So what we want to do, I want to look at this and say, hey, look, if I go from here to here and find this area, then I can use symmetry to get that area. So that's exactly what I'm going to do. Now starting here, this is going to be theta equals 0. And when I come around to this point, this is actually theta equals pi over 2. So what I'm going to do is I'm going to take a look at twice the integral. Yeah, I'm going to change that just a little bit. I need a bracket in here. I'm going to put twice 1/2 the integral from 0 to pi over 2 of cosine squared of 3 theta d theta. And that should do it for me. Well, obviously my 2's are going to cancel, so this could be equal to the integral from 0 to pi over 2 of cosine squared of 3 theta. I'm going to rewrite that. That's going to be 1 plus cosine of 6 theta over 2 d theta, which I'm going to rewrite one more time. I'm going to pull out this 1/2. So this is going to be 1/2 times the integral from 0 to pi over 2 of 1 plus cosine of 6 theta d theta. Now that is going to be equal to 1/2 times theta plus, obviously I'm going to have a sine of 6 theta, but the derivative of sine of 6 theta is going to be 6 cosine of 6 theta, so I need to divide this by 6. Then of course evaluate that from 0 to pi over 2. So that's going to be equal to 1/2 times theta is going to be pi over 2 plus sine of 6 theta is sine, I'll write that in there, sine of 6 times pi over 2. That's the same as sine of 3 pi. This piece right here is 0. Minus, this next piece is going to be 0 plus 0. So this is actually equal to pi over 4. And remember, I multiplied it by 2 right here, so I found this, and I multiplied it by 2 so I could actually get all of that.